Modern systems engineering aims to achieve horizontal elasticity, a state where compute supply automatically and continuously maps itself to real-time workload demand. The primary mechanism for this is the Amazon EC2 auto-scaling group. This is a logical boundary that manages a collection of EC2 instances, expanding or contracting the fleet based on defined traffic conditions. This elasticity relies on a telemetry loop. Every active EC2 instance in the group is streaming performance metrics, such as CPU utilization or network I/O, directly to Amazon CloudWatch. CloudWatch aggregates these metrics across the entire fleet to compute an average. We can then establish an alarm that triggers if the total fleet utilization exceeds a threshold of 80%. When that alarm triggers, the auto-scaling group executes a scale-out policy. The engine automatically provisions and boots a fourth instance to distribute the excessive processing load. To optimize the compute budget, we implement a corresponding scale-in policy. If the average CPU utilization drops below 30%, it signals that we have idle capacity. The auto-scaling group then terminates the redundant nodes in a controlled sequence, ensuring we pay only for the compute power required at that moment. This closed-loop system allows the compute tier to track the curve of incoming traffic, balancing application performance with strict cost efficiency. We can see this loop in action by analyzing a stateless application architecture, such as a time query service like whatisTheTime.com. Because the code requires no local session storage, it can scale horizontally without complexity. The network path begins when a user's browser sends a DNS query. Amazon Route 53 resolves that query by returning an alias record, pointing to a regional elastic load balancer. The request reaches a multi-AZ elastic load balancer, which is continuously performing health checks to ensure it only routes traffic to functional targets. The load balancer then passes the request to the auto-scaling group. In this configuration, the group spans 3 distinct availability zones: AZ1, AZ2, and AZ3. This provides hardware fault tolerance. If AZ1 suffers a total physical failure, such as a localized power outage, the application remains available. The load balancer automatically reroutes traffic to the surviving zones, and the auto-scaling group provisions new instances in AZ2 and AZ3 to replace the lost capacity. While this ensures uptime, managing large-scale fleets requires a financial strategy to handle the cost of constant baseline traffic. By setting the minimum capacity of the auto-scaling group to the baseline traffic level, we can use reserved instances. These provide a significant discount for the compute power we know we will always need. The auto-scaling group then uses standard on-demand instances strictly to handle the unpredictable traffic spikes that rise above that baseline. This combination of reserved baseline capacity and elastic on-demand scaling provides high availability without exceeding the operational budget. Most production applications, like e-commerce platforms, are more complex because they must track stateful data, such as a user's shopping cart. If we store user sessions in the local RAM of an individual EC2 instance, the data is trapped. Scaling out becomes difficult because a user session is tied to one specific piece of hardware. Using sticky sessions to force a user to stay on one instance is a risk. If that instance is terminated by a scale-in policy, we run the risk of losing the user's data. To maintain elasticity, we must extract the session state from the compute layer and move it to a dedicated external storage tier. In this model, the application writes session state directly to an Amazon ElastiCache Redis cluster rather than its own local memory. To ensure the cache itself is resilient, we deploy ElastiCache in a multi-AZ configuration. Now, whichever instance receives the next request simply queries ElastiCache to retrieve the current session state. Meanwhile, persistent transactional data, like order history, is stored in an Amazon RDS relational database. Like our other components, RDS utilizes multi-AZ standby for failover and read replicas to scale the database's read performance horizontally. By offloading sessions to ElastiCache and transactions to RDS, EC2 instances become stateless units that can be scaled or terminated without data loss. One final scaling challenge is shared storage. Content-heavy applications need a way for multiple instances to access and synchronize static assets like images or videos. A standard Amazon EBS volume is a block storage device locked to a single availability zone. It cannot be mounted by multiple instances across different zones simultaneously. If the autoscaling group launches a new instance in AZ2, that instance has no way to access the files written to an EBS volume in AZ1. To solve this, we use Amazon Elastic File System, or EFS. EFS operates by deploying mount targets, which are logical elastic network interfaces, into each subnet of your VPC. This allows instances in all 3 availability zones to mount the shared file system simultaneously, using the NFS v4.1 protocol. EFS is serverless and scales its capacity automatically as you add files, meaning there is no need to manually provision disk space. By moving from localized block storage to regional network file storage, we eliminate the synchronization bottleneck that often limits horizontally scaled clusters. AWS Elastic Beanstalk is a managed orchestration service designed to automate the deployment of these layers directly from your application code. Beanstalk offers 2 primary deployment modes. Single instance mode provisions one EC2 instance with an elastic IP and a local database. Because this mode provides no scaling or failover capabilities, it is used only for rapid prototyping and testing. High availability mode is the standard for production. It instructs Beanstalk to build the resilient architecture we've discussed. It automatically provisions the elastic load balancer, configures the autoscaling group across multiple zones, and sets up RDS with multi-AZ replication. This managed deployment builds on the foundations of hardware fault tolerance established by isolated physical availability zones. It utilizes the network traffic orchestration and security group isolation provided by managed elastic load balancers, and it achieves elasticity by deploying stateless compute fleets governed by CloudWatch telemetry and supported by decoupled storage tiers. Combining isolated data centers, managed networking, and automated stateless compute results in a system that absorbs hardware failures and tracks workload demand without manual intervention.